Namaskar, welcome to the channel Anka Ananda Aharan, that is extracting happiness from the teaching learning process of mathematics. Today we are going to discuss about chapter 6, chapter 7, some of the aspects of chapter 6, chapter 7 of Gilbert Strong book, that is applied linear algebra, that is linear algebra and its applications. So today we are going to discuss about positive definiteness. So before discussing positive definiteness, we should know about what do we mean by quadratic form. The quadratic form of a given matrix, the given square matrix A is given by X transpose AX. Here A is a real matrix. So how to find out the corresponding quadratic form? Here, to find out that X transpose AX, this is the X transpose, that is x1, x2 as written in this format. Now, we will find out what is its value. Observe this, these are the diagonal elements of A. So, 1, 1 will be x1 square. So, the coefficients will be A11 x1 square plus A22 x2 square plus A33 x3 square plus A12 plus A21 into x1 x2 plus A13 plus A31 into x1 x3 plus A23 plus A32 into x2 x3. That means the position depends, gives the variables. 1 to 2, 1 position will have the variables x2 x1 x2. 1 3 3 1 will have the variables x1 x3. 2 3 3 2 will have the variables x2 x3. So this is all about quadratic form of a given matrix. Now consider these two 2 cross 2 matrices. How to find out the corresponding quadratic forms. So here this is x1 transpose AX is equal to 1 into x1 square plus 5 into x2 square plus 3 plus 3, that is 6 into x1 x2. Similarly, for B it is 1 x1 square 1 plus 1 x2 square minus 2 x1 x2. Similarly, for C it is 2 x1 square plus 5 x2 square plus 3 plus 3, that is 6 x1 x2. Similarly, in case of D, the quadratic form is minus x1 square plus minus 8 x2 square plus 4 x1 x2. So these are all written here. One can verify. Now let us write down the corresponding matrix of the quadratic form. So here the coefficient of x1 is this one, coefficient of x1 square is this one, coefficient of x2 square this one, coefficient of x3 square is this one. Similarly, x1 x2 is divided into two parts. One is kept here, another is kept here. Coefficient of x1 x3, half part kept here and half part kept here. So coefficient of x2 x3 is partially, half is kept here, another half kept here. So we got the matrix. Similarly, this one is the diagonal elements of the matrix are 1 to 11 and 1 to 2 1 position are having minus 1 minus 1, 1 3 3 1 position minus 2 minus 1 minus 1 and 2 3 3 2 position minus 2 minus 2. Observe the same. So here we could know from a matrix how to write down the quadratic form, from a quadratic form how to write down the matrices. Now there are possibilities when all these quadratic forms can be positive, negative depending on the type of matrices, because these quadratic forms are scalar values. Now what do we mean by a positive definite matrix or positive definiteness of a given matrix? A real symmetric matrix is said to be positive definite if any one of the following holds true, out of which this diagonal is the easiest way to verify. So here the quadratic form x transpose Ax is always positive for all non-zero real vectors x, or all eigenvalues of A are positive, or all upper left submatrices AK have positive determinants dk for all k. So here observe what about the upper left submatrix 1 1. Here it is. You just observe the diagonal elements, just increase the diagonal elements by 1. So we will get our matrix. So this includes, this smallest one includes one diagonal element, here two diagonal elements, here three diagonal elements, and the final one all the diagonal elements. So it is 4 cross 4 matrix. So if all the determinants of all the matrices are positive, then it is positive definite. And some are positive, some are zero, then it is positive semi-definite. If all are negative, negative definite. Some are negative, some are zero, negative semi-definite. Some are positive and some are negative, indefinite. Such matrices are said to be indefinite. Here are the conditions. Positive semi-definite means if I am verifying for eigenvalues, all eigenvalues may have non-negative values, either positive or negative, positive or zero. It allows, means if lambda is greater than equal to 0 or the decays are greater than equal to 0, means some of them are positive and some are 0, then it is positive semi-definite. What about negative definite? That is, all eigenvalues are strictly negative, or all quadratic forms are strictly negative, or all diagonal that left corner, upper left corner diagonal matrix determinant all are negative, then it is negative definite. Some are negative and some are zeros, it is negative semi-definite. And some are positive and some are negative. In that case, it is indefinite. Now let us verify some of the matrices. Decide for or against the positive definiteness of the given matrix A. Here A is given by 2, minus 1, minus 1, minus 1, 2, minus 1, minus 1, minus 1, 2. So here this is my diagonal D1, which is 2, which is positive. Then determinant of this matrix is my D2, which is 3, which is positive. Then the determinant of whole matrix is my D3. And what is being found? Its value is 0. That means some are positive, some are 0. That means it is positive semi-definite. That means it is not positive definite. So the given matrix is not positive definite. A is not positive definite. It is positive semi-definite. Next, B. Here D1 is 2, this is 2, and this matrix determinant is 3. The whole matrix determinant is 4, which is positive. So here D1, D2, D3 all are positive, hence B is positive definite. Now let us discuss about C. Here observe C is square of a symmetric matrix. Let that symmetric matrix be F. As F is symmetric, all its eigenvalues are real. And as determinant of F is equal to 4, which is non-zero, that means all the eigenvalues of F are non-zero real numbers. So eigenvalues of C are square of eigenvalues of F, which are always positive values. Because square of real numbers are always non-negative, and as the eigenvalues of F are non-zero, so we have all the eigenvalues of C are strictly positive. So C is positive definite. In this way we can do it. It is logically we are discussing. Suppose we will just go for simple algebra. Then we have to multiply f with itself. We will get a matrix. We will find out it's d1, d2, d3, and then we will decide, and finally the decision will be C is a positive definite matrix. But if we are going through logic, it gives better idea about the subject. Now let us discuss about singular value decomposition. What do we mean by singular value decomposition of a given matrix? Let us consider a matrix A which is having m rows and columns. That means its eigenvalues cannot be obtained, neither the eigenvalue decomposition of this matrix can be obtained, as it is not a square matrix. So what we will do for such a matrix? We will go for singular value decomposition. We will obtain two matrices which are square matrices from the given matrix. So the singular value decomposition of A is given by U sigma V transpose, where U is a m by m orthogonal matrix, sigma is m by n rectangular matrix, and not necessarily rectangular. Here it is rectangular, so that's why rectangular. Whatever A maintains, the same thing will be maintained in sigma. And what about V transpose? V transpose means it is the transpose of a matrix, an orthogonal matrix, which is having n rows, n columns. How to find out U, V, sigma? Let us discuss. First, we will find out the eigenvalues of out of A, and we have to verify which is of a lesser order. So here A is having m by n. So first what we will verify? We will verify m is less or n is less. Let us assume m is less. Then we will find out A transpose matrix first. If m is larger, then first we will find out A transpose. The smaller matrix we will study first, because its eigenvalues and eigenvectors can be very comfortably obtained. If for a smaller matrix we obtain the smaller means matrix of less order or lower order. Okay. So if it has lesser number of rows and columns, then in that case it will be easy to find out the eigenvalues and the other eigenvalues. So here we have one information with us, that the eigenvalues of a given matrix, observe here, the eigenvalues of a given matrix A, for A transpose and A transpose A, both these matrices have same non-zero eigenvalues. That means if at all they are having different eigenvalues, the different eigenvalues are zero values. So this matrix is having lesser number of rows and columns. For that matrix, we will first calculate the eigenvalues. We will arrange them in descending order. That is, largest eigenvalue will be the first eigenvalue, next little bit smaller, next. Likewise, in decreasing order, we will arrange the eigenvalues. And then we will find out the corresponding eigenvectors. Let x1, x2 and so on up to xm be the eigenvectors of, here eigenvectors of A transpose for lambda 1 to lambda m respectively. Then we will find out, we will normalize them to find out ui. Ui is equal to xi by norm of xi. And from there, we will write the matrix U, which is orthogonal matrix. How to find out? So here, this U1, U2, all these things, we will write as columns. So from here, we will get the UI vector, and writing U1, U2 systematically, the first vector should be corresponding to the largest eigenvalue, second vector, second largest eigenvalue. Likewise, we will arrange the vectors. Then we got our U. Similarly, from the eigenvalues of A transpose A transpose, we will find out the eigenvalues of A transpose A. Here, all the non-zero eigenvalues are same. The other eigenvalues which are different, they are just zero eigenvalues. So again here we will find out eigenvalues of A transpose A. Then we will arrange them in descending order. Then we will find out the corresponding eigenvectors y1, y2, y3 and so on up to yn for the matrix A transpose A. Then we will normalize them to get normalize the eigenvectors of A transpose A to get to Vi. So now V is equal to V1, V2, V3 such that V1 corresponds to the largest eigenvalue, V2 corresponds to the second largest eigenvalue, likewise. Vn represents the smallest eigenvalue. So I got the matrix V. Already I have the matrix U. Now I will get the matrix sigma. So what we will do? A, according to the number of rows and columns of A, we will first write the matrices. Then in the descending order, we'll write the diagonal position elements. How we will write? The largest eigenvalue's square root is the first singular value. Second singular value from this relation, okay, from this relation, that is sigma I is equal to square root of lambda I. So from there we will find out the values of sigma and we will write them in the diagonal positions, and rest all values will be all entries will be zeros. So like this we will write sigma. So we have U, V, sigma. Now from V we can find out V transpose. So we will substitute the value of U, V and sigma in the formula this. This is our formula. So in this formula we will substitute the values and we will get the SBD of A. Then after getting the SBD, we have U, V, sigma. We will use this formula to find out the pseudo inverse. So here how to get the sigma? Sigma plus is the matrix obtained from the transpose of sigma by replacing all the non-zero elements by their reciprocals. So for example, suppose I have a matrix sigma. Suppose I have a matrix sigma is equal to 5, 2, 0, 0, 0, 0. This is my matrix sigma. Then what will be sigma plus? This is 1 by 5, 1 by 2, rest all will be 0, 0, 0. So first I have transposed the given matrix, then the values which are having non-zero values there, those values are replaced by the reciprocals. So like this I will get my sigma plus. After getting sigma plus and substituting there in the formula, observe here the formula is written here. In this formula we will substitute to get our, and after multiplication we get our pseudo inverse. And if any matrix inverse exists, for a matrix whose inverse exists, the pseudo inverse is nothing but the inverse itself. For a matrix whose inverse exists, A plus, that is pseudo inverse, is equal to A inverse. Okay. Now using this pseudo inverse, so that's why suppose I have a system of equation X is equal to B, whether it has solution or not, From there, I can find out x using the formula a plus b. So here, using this formula directly, we can find out the pseudo-inverse. So any system of equation, whether it has solution or not, we can find out an approximate estimate of the solution, that is using the pseudo-inverse concept. Now some problems from the book. How to do? Here given A is this one, we have to find out the SBD of A and pseudo inverse of A. So to find out SBD, A transpose is nothing but 1 cross 1, that is 4. So here it is 1 cross 1, 1 cross 4, 4 cross 1, it is 1 cross 1, that is 4. So I got a matrix having only one element. So that one element is the eigenvalue of A transpose. So what about the eigenvector? Eigenvector means 4 A into A transpose minus 4I into X is equal to 0. So in place of lambda, substitute 4. What we are getting? It is 4 minus 4 into x1 is equal to 0. So x1 is equal to arbitrary, that is x1 is equal to 1. So 1 is a normalized eigenvector of A transpose. Now we will go for the other matrix, that is A transpose A, which is a 4 cross 4 matrix. Observe here, sum of all the diagonal elements are 4. Sum of all the diagonal elements are each 4, that is 1 plus 1 plus 1 plus. So it is 4. So here we know that A and A transpose and A transpose A share the same non-zero eigenvalues. So eigenvalues of A transpose A are 4, the only non-zero element, and rest all are 0. So 4, 0, 0, 0. 3 zeros are there. That means algebraic multiplicity of this 0 is 3. So from there, let us find out the eigenvectors. We are expected to get the 3 eigenvectors. So lambda is equal to 0 means nothing is subtracted from the diagonal element. So A remains as it is. So this into y1, y2, y3, y4 is equal to 0. From the echelon form, it can be written in this format. So here, from this equation, what we got? We got y1 plus y2 plus y3 plus y4 is equal to 0. So here only one pivot is there. So that is y1 is a pivot, rest all are free. So 1, 0, 0, 0, 1, 0, 0, 0, 1. Substituting here in this equation of the value of y2, y3, y1, y2, y3, y4, we got y1 is equal to minus 1, y1 is equal to minus 1, and this minus 1. So we got our vectors. So it is this vector, then I wrote this vector, then I wrote this vector. So these are the 3 eigenvectors of A transpose A for lambda is equal to 0. Now for lambda is equal to 3, from the diagonal elements will reduce 4 or subtract 4. So the diagonal elements will be minus 3, minus 3, minus 3, minus 3. Now by row interchange and applying elementary row operations on it, we get the matrix is equivalent to this matrix. So here 3 pivots are there. So only one variable, that is free variable, is my y4. So I will substitute y4 is equal to 1. This value I have substituted. Now minus y3, 2y3 plus 2y4 is equal to 0, which implies y3 is also equal to 1. Now from this equation, from this third equation, we will get y2 is equal to 1, and from this equation, from first equation, we'll get y1 is also 1. So the eigenvectors corresponding, the linearly independent eigenvectors corresponding to eigenvalue is equal to 4 is this one. So it is not normalized. What about the normalized eigenvector then? In that case, every component is divided by square root of 1 plus 1 plus 1 plus 1. That is square root of 4, that is half. So this is my first, it corresponds to the first eigenvalue, largest eigenvalue, that is 4, and these 3 corresponds to eigenvalue lambda is equal to 0. So this is V, I got V, I got U, and what about sigma? Sigma here only one non-zero eigenvalue is there, so its square root is singular value sigma 1 is equal to 2. So this is the required SVD of A. This is the SVD of A. Now as this is SVD of A, we can find out its pseudo inverse, and the pseudo inverse is found to be, substituting in this formula, the pseudo inverse is given to be this one, that is 1 by 4, 1 by 4, 1 by 4, 1 by 4. So with this, some of the problems associated with this video we have done. One problem we have done. Now let us do another problem, that is, consider a matrix B is equal to this one. So what about B transpose? It is 2 cross 2 identity matrix. What about B transpose B? It is the matrix which is written here. Okay, so it is of order 3 cross 3, it is of order 2 cross 2. So first we will find out the eigenvalues of, but this matrix B transpose matrix is a diagonal matrix, hence the eigenvalues are the diagonal elements. So lambda is equal to 1 is an eigenvalue with multiplicity 2. So I am expected to get 2 linearly independent eigenvectors. So for lambda is equal to 1, for lambda is equal to 1, this minus lambda is 1. So what will happen, that from the diagonal elements already ones were there and we will reduce it, that one, so it is the diagonal elements will be 0. Now for any 0 matrix, whatever matrix I will multiply, whatever vector I will multiply, I will get 0 vector. That means here both the variables are free. So this is free, this is free. So we have substituted here 1, here 0, here 0, here 1. It is not necessary that every time we will be writing the sequence like this. Sometimes if necessary, we can change the order. As both of them are corresponding to one eigenvalue lambda, so whether this vector I am writing first or whether this vector I am writing first, they are not having much impact. But for our problem, we must write like this. So let this is my u1, or this is my u1, and this is my u2. Why I am changing the order? Observe here. The later part we will discuss. When we'll find out the eigenvectors of B transpose B, then we will discuss. So for B transpose B, the eigenvalues are 1, 1, 0. So for lambda is equal to 1, we are getting 2 linearly independent eigenvectors. They are given by these 2 vectors. So it is my y1, it is my y2. Now for lambda is equal to 0, we will not subtract anything from the diagonal element, so it remains same. So this vector in this matrix into this vector is equal to 0. So here two are free. Sorry, this is pivot. This is pivot. Only one variable is free, that is y3. Let us substitute that. So y3 is free, so I have assigned value 1 to it, and the previous two values were pivot variables where we got the values are from the equation. It is y1 is equal to 0 and y2 is equal to 0. So the eigenvector corresponding to lambda is equal to 0 of the matrix B transpose B is given by 0, 0, 1. Now the SVD of A is equal to U sigma V transpose. Observe here the U which I have written here is 0, 1, 1, 0. This is my first eigenvector. This is my second eigenvector. Specifically, why I have changed the order? Because observe, when I will write my sigma, how the sigma will be? Largest eigenvalues square root. So 1's square root is 1. So this value and this value should be written here. But after multiplication, and V is all the components of V. Observe, all the columns are there. They are orthonormal sets of vectors. So here V transpose is nothing but V. So I wrote it. But this is identity matrix. That means these two matrices after multiplication, I will get this matrix. And if it were identity matrix, then what I will get? I will get the same matrix written here. But I require the matrix should be having rows interchanged. Observe. What was the matrix written here? It is 0, 1, 0, 1, 0, 0. From the very beginning it is there. Observe here. 0, 1, 0, 1, 0, 0. That means the central matrix, sigma matrix, rows must be interchanged. So to achieve that state, what is expected? We will change the orders of the columns of U. So now observe here, in case of U, this is my first row, this is my second row. How I obtain it from the identity matrix? By interchanging the first rows. So now when I multiply this, I will get this matrix. And now when I multiply from the left hand side by a row matrix, what we will get? We will get the rows are interchanged. So it is 0, 1, 0, 1, 0, 0. So what I get? I get my required matrix A. But if instead of 0, 1, 1, 0, we are reversing the orders of the columns, that is, this we will make first column and this I will make second column, then I may not get the product multiplication of these three matrices is equal to A. So here we must focus in one thing, that the matrices considered should be in reverse order. So I should write 0, 1, 1, 0. Okay, now I got this one. Then what will be my pseudo inverse? My pseudo inverse is A plus is equal to V sigma plus U transpose. V is written as it is, sigma plus, that means the rows are converted to columns, columns are converted to rows, and the non-zero elements are replaced by the reciprocals, but once reciprocal is 1, so it will remain same. Then here, this is my U. Now, whenever U will be multiplied with sigma, what I am getting? There will be a row interchange. But this is identity matrix, so no impact. Finally, this product is equal to this much. Therefore, the pseudo inverse of A, which is equal to A plus, is equal to 0, 1, 0, 1, 0, 0. Okay. So with this chapter we will conclude. Now we'll go for the next chapter, condition number 9. Okay. Now what about the condition number n norm? Let us define that first. Okay. Norm of a given matrix. For a given matrix A, norm of A is equal to square root of lambda max of A transpose A. That means find out the eigenvalues of A transpose A, and the largest eigenvalues square root is my norm of A. Similarly, what is norm of A inverse? It is 1 upon lambda mean of A transpose A. Once we got these two, the condition number C is equal to norm of A into norm of A inverse. So here how much it is? It is lambda max by lambda mean whole root over of A transpose A. But for a positive definite matrix, A, what about the eigenvalues then? Positive definite. If it is positive definite, then only you can apply this formula. So lambda norm of A is equal to lambda max of A, and norm of A inverse equal to lambda mean of A. So C is equal to lambda max by lambda mean of A. Okay, so we got the formula for this. So for positive definite we got for positive. Now question number 15 from the book. What it is telling us? Find out the eigenvalues, condition number norm for the given matrices. The question number 15 is, just a second. It is C A is equal to 100, 0, 0, 2. It is a diagonal matrix. So diagonal elements are the eigenvalues. So and it is symmetric, and all the eigenvalues are lambda 1 is equal to 100, lambda 2 is equal to 2. So all the eigenvalues are positive. So A is positive definite. Why it is positive definite? Because A is symmetric with all eigenvalues positive. So for positive definite matrices, how to find out A norm is equal to lambda max of A, which is equal to 100. Similarly, what will be A inverse norm? This is 1 by 2 mane that is 1 by 2 means that is 1 upon lambda mean of A. The value is 1 by 2. So C is equal to norm of A into norm of A inverse, that is equal to 100 into half is equal to 50. Now the question is, similarly we can find out the other eigenvalues for B, C, D. All of them are positive definite matrices. So very comfortably we can find out. Now what about the, first let me do the other problems, then we will come to this problem. Okay. So the B matrix is given as B matrix 2, 1, 1, 2. It is a symmetric matrix and the determinant is, so this is positive, so D1 is equal to 2 is positive, D2 is equal to 3 which is positive, and B is symmetric, B transpose is equal to B. So this implies B is positive definite. As B is positive definite, directly we can find out the norm of B and B inverse. So what is norm of B? Is equal to 1 by lambda max. Sorry, first of all we have to find out the eigenvalues. So the eigenvalues of B are given by the CH equation. What about the CH equation? Lambda square minus 4 lambda plus 3 is equal to 0. So lambda is equal to 3, lambda is equal to 1. So what about the eigenvalues? So norm of A is equal to lambda max of A, that is equal to 3. Norm of A inverse is equal to 1 upon lambda mean of A, that is 1 by 1, that is 1. So C is equal to norm of A into norm of A inverse, that is equal to 3 into 1, that is 3. Okay, now what else? C is given by, where is the matrix C? Here directly D is written, but I will write it C. Okay. Oh, D, why D name is written? Because C term we will use in the condition number. That's why the name given is D. The name I have given. Okay. So this is my matrix D. It is symmetric and the determinant is positive. 3 is positive. So here it is symmetric. D1 is equal to 3. D2 is equal to 2. Both are positive. And D transpose is equal to D. Hence D is positive definite. So what we will do then, once it is positive definite, what about the eigenvalues? The CH equation of D is lambda square minus 4 lambda plus 2 is equal to 0. So lambda is equal to 4 plus or minus b plus or minus b square, 16 minus 8 whole root over by 2. What are these values? They are 2 plus or minus root 2. So here, what about the norm of A? Norm of A is equal to lambda max of A, that is equal to 2 plus root 2, and A inverse is equal to 1 upon lambda mean of A, that is equal to 2 minus 2 inverse. So what about the condition number? The condition number C is equal to 2 plus root 2 by 2 minus root 2. Okay. Next, we will go for the values or matrices which are not positive definite. In that case, what will happen? We have to find out the eigenvalues of both the matrices. The eigenvalues of A transpose A, and from their maximum value, minimum value, we will find out the condition number and norms. Okay, just let me clear it so that we can do few more problems. Okay, so now the question is question number 17. What does it indicate? A is given by a matrix which is not positive definite. Question number 17. It is minus 2, 0, 0, 2. It is a diagonal matrix and the diagonal elements are the eigenvalues. The eigenvalues are minus 2 and plus 2. That means it is indefinite. That means the matrix is not positive definite. It's a positive. It is indefinite matrix. So here what we require? A transpose A we require, which is the matrix multiplied with itself, because it is a symmetric matrix. So it is two diagonal matrices are multiplied, means it is minus 2, 0, 0, 2 into again same matrix, because it is symmetric matrix. So directly I could have written, but for the students may have confused, that's why I wrote. So the diagonal elements are multiplied with themselves. So we got this one. So now here the eigenvalues are, so lambda max, now the eigenvalues of A transpose A are 4, 4. So lambda max is 4, lambda mean is 4. So A norm is equal to lambda max square root of A transpose A, which is equal to square root of 4, that is equal to 2. And A inverse is equal to 1 upon lambda mean, that is minimum, of A transpose A, that is equal to square root of 4, that is equal to 2. 1 by 4, it is 1 by 2. So C is equal to condition number is equal to norm of A into जगह into norm of A inverse. Okay, so what we got? This is equal to how much? 2 into half is equal to 1. Okay, so for this matrix it is over. Now next is B matrix 1 1 0 0. Another matrix B is equal to 1 1 0 0. It is not symmetric, so there is no question of positive definiteness. So here what about B transpose? It is 1 1 0 0. Then what about B transpose? B transpose B is equal to how much? The matrix is 1 1 1. You can verify using your calculator or you can calculate by yourself. Okay, so we got these are two eigenvalues, sorry, this. So what about the CH equation? Lambda square minus 2 lambda, determinant is 0, so is equal to 0. So eigenvalues are lambda 1 is equal to 2, lambda 2 is equal to 0. So norm of B is equal to square root of lambda max of B transpose B, that is equal to square root of 2. And what about the norm of B inverse? Norm of B inverse is 1 upon lambda mean square root over, that is 1 upon square root over 0, that is equal to infinity. So C, which is condition number, what's the condition number? This is equal to norm of B into norm of B inverse, that is equal to root 2 into infinity, that is infinity. Okay, so like this, any problem given, we can simplify and find out the condition number and norm of any given square matrix. Next we will go to matrix, a new topic, that is matrix of an iterative method. To solve Ax is equal to B. So here the iterative method depends only on A. So to find out that matrix, we require only A. From A, we will find out that matrix. So what we will do? Step 1, write A is equal to lower triangular matrix plus diagonal matrix plus upper triangular matrix. Then find T is equal to S minus A and find M, that is equal to S inverse T. Here M is the matrix required for the given method. For today we will discuss two methods. For both the methods up to this much it is common. Then we will go for methods. For Jacobi method. S is equal to D, which implies T is equal to minus L minus U. So M is equal to minus of D inverse L plus U. And for next page we will do here. For Gauss-Seidel method, S is equal to L plus D, which implies T is equal to minus U, which implies M is equal to S inverse T, that is minus of L plus D inverse into U. Okay, these are the two methods. Now using these two methods, we are expected to find out the matrix where A is given by whatever our given A is given by 2, minus 1, 0, minus 1, 2, minus 1, 0, minus 1. This is my A. So clearly I can write them as L. When I am writing L, diagonal elements and above the diagonal elements, everything I will make 0. So here minus 1, this 0, this. Okay, this is my L. Plus, what is my D? 2, 2, 2. Rest all elements are 0. It is my D. What about U? Diagonal elements and lower diagonal elements all are 0. Just upper part we will copy from the matrix. So this is my U. It is my D, it is my U. Now for Jacobi method, what is my M? M is equal to how much? Jacobi method minus D inverse L plus U. So that is minus D inverse means diagonal elements. Any diagonal matrix has its inverse, all the diagonal elements replaced by their reciprocals. So it is D inverse. Then L plus U, that is the diagonals are 0. Here it is minus 1, 0. It is minus 1, minus 1. Sorry. It is 0, it is minus 1. Now this is L plus U. But this minus and these minuses, everything I have made plus after multiplying. So we know when a scalar matrix is multiplied to a given matrix, each element of that matrix is multiplied by that scalar. So how much it is? 0, half, 0, half, 0, half, 0, half, 0. So every element I have multiplied by half. Very comfortably I wrote. So this is my target for Jacobi method. Now suppose in the examination Seidel method is asked. Then for Gauss-Seidel method, what we will do? Here what's the formula? Okay, for Gauss-Seidel method, whatever the formula, it is m is equal to minus of L plus D whole inverse into U. So now minus of, what is L plus D? 2, 2, 2. Here it is minus 1, 0, minus 1. This is L plus D. Its inverse into U is 0, 0, 0, minus 1, 0, minus 1. Rest all are 0. This is U. Okay. Now using calculator or using Gauss-Jordan method or any other method, one can find out the inverse of this matrix. And what about the inverse? It is this negative, this negative, they took care of each other. Okay, now this matrix inverse. It is half, 0, 0, 1 by 4, half, 0, 1 by 8, 1 by 4, 1 by 2. 1 by 2 or what? I have to verify for the last element. Okay, let me write down this, then finally we will verify. This into how much? 0, 0, 0, 1, 0, 0, 0, 1, 0. This matrix will multiply. So the answer is this row into this column 0, this row into this column 0, this row into this column 0. Now this row into this column half, it is 1 by 4, it is 1 by 8. Then here this row, this column 0, half, it is 1 by 4. Okay, so this is the answer. Here I have a doubt, just we will clarify the doubt. Okay, the matrix is just the inverse. I have doubt about the inverse. Let us apply Gauss-Jordan method to find out the inverse. So this is the answer. Here the answering is over. You can calculate in the examination. You can calculate the matrix inverse by your calculator also. But let me verify using Gauss-Jordan method. 0, 0. It is minus 1, 2, 0. Then it is 0, minus 1, 2. 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, it is what I will do. First row I will divide by half. So 1, 0, 0, half, 0, 0. It is Now this is added with this row. How much it is? It is 0, it is 2, it is 0, it is 1 by 2, it is 1, it is 0. And similarly here already 0 is there, nothing to be done. Minus 1, 2, this is 0, 0, 1. Now what I will do? I will divide it by 1. Third row and second row will divide it by 1. How much is it? Divided by 2. How much it is? It is 1, 0, 0, half 0, 0, 0, 1, 0, 1 by 4, 1 by 2, 0, 0, minus 1 by 2, 1, it is 0, 0, 1 by 2. So here what we will do? We'll multiply second equation by half and we will add it to third. So how much it is? 1, 0, 0. It is half 0, 0. It is 0, 1, 0. It is 1 by 4, 1 by 2, 0. Now we will multiply the second row by half and add it to third row. So how much it is? 0, 0, 1. Half means it is 1 by 8. Half means 1 by 4. Here half. Okay, correct answer is written. So I was having confusion about the inverse. So this is the inverse which we have substituted. Observe here. This is the inverse. So we have written it correctly. So with this, our preparation hints for the examination is over. Let me clarify. There are infinite number of errors while pronouncing and writing, but it can be felt by the audience or viewer if they are involved while discussing or observing or analyzing the videos. So, the main purpose is to give some hint about how to prepare for the examinations. All the best for your examinations. If any error is found, please rectify while answering by yourself. Whenever you found that it is erroneous and you can experience that it is what is the correct answer. So please rectify while writing. Thank you for your patient listening. With this, all the best for your exams.